All right, those of you who braved the elements out there, I mean vacation out there, why don't we get started? Are there any questions? We're gonna continue talking about colloids and less about the structure and more about the consequence today. But we're gonna just sort of get everybody back to par, where what we mean by this structure, and more importantly, the consequence of this structure. Because from our perspective, it's really cool. Don't get me wrong. I think it's totally cool, the crystalline structure, building. I mean, it's like puzzle pieces, putting things together. But some of you are like, no, it's not. It's terrible. No, but what's really, really cool about this is these structures and the natures of these structures really affect the charge of these structures. And when we start talking about nutrients later on, in fact, we're going to start talking about some of it today, it's these charges, these charged particles that are basically driving much of the nutrient behavior in the soils. If I have a charged particle, a magnet, the soil, colloid, in the soil, and then I put a charged ion in that happens to be a nutrient, okay, whether it's a positively or negatively charged ion, it's going to interact with that colloid. And that colloid potentially will hold that particle there, that ion there, for later use. In essence, this is the storage capacity. Think of this sort of as a bank. This is the storage capacity of soils to hold on to these nutrients, ions and cations, these nutrients that are in the soil solution. So they're not lost with the water as the system moves. Does that make sense? So today's lecture is really, okay, we're gonna touch base on what these colloids are, and we're going to talk again about what the nature of these colloids are. But what we're going to do is we're going to be moving into what's the consequence of this. And if we talk about these materials weathering and just we're fertilizing and we have stuff coming in from the atmosphere and we have decomposition going on, you certainly have an understanding that these ions are going into that solution, but what's happening to them in solution? Okay? So back to the colloids. We have 4 different types. We have the phyllosilicates. We have the non-crystalline or the amorphous silicates. We have the iron and aluminum oxides. And then we have the colloids, the organic molecules. Okay. All of these are charged. And all of them are charged at different rates and at different pHs, or at different intensities and at different pHs. Okay? These charges, there's basically 2 types. One is the constant charge and one is the pH-dependent or variable charge. The constant charge is associated with the structure. It's due to the nature of that structure. When we're talking about the phyllosilicates, we're looking at that isomorphic substitution, that charge imbalance that's part of that structure. And that's why we talked about how these things were put together, how they were built. Okay? We also have this variable or pH-dependent charge. This is both positive and negative. Generally, when we talk about isomorphic substitution, we generally think of this as a negative charge, but we can in fact have positive charge, but it is predominantly negative. pH dependent can be predominantly negative or predominantly positive depending upon what the pH is. Okay? It's primarily associated with those hydroxide molecules that are sticking out from the colloid that are sticking out into the soil solution. It's what's exposed, okay? And it is the primary source of charge on humic materials and iron and aluminum sesquioxides, as well as aliphanes and some of the phyllosilicates. Do you guys remember which phyllosilicate? It would be the phyllosilicate that has the hydroxide exposed. So all of them have the hydroxide exposed at the edges. But it's not until that octahedral sheet gets exposed when the tetrahedral sheets start weathering away that those oxygens are basically out into the soil solution. So in essence, the 1-to-1 phyllosilicates versus the 2-to-1 or the 2-to-1-to-1s. Does that make sense? I showed this picture before, but this basically shows you the different types of minerals. Okay, so we're looking at the less weathered minerals over here to the more weathered minerals over here. We're also looking at, in essence, more isomorphic substitution here than here. There's weathering But as these things weather, much of that isomorphic substitution starts to disappear. The minerals become more pure. I don't really like that term, but does that make sense? Okay? And here you can see where the isomorphic substitution is, whether it's in the octahedral sheets or the tetrahedral sheets. Okay? And here you can literally see the charge that's associated with that single building block that's going to build up the larger sheets. Okay, so here's the charge. Okay, let's hold off on that. I showed this again just because I wanted you guys to see this sort of variability. Okay, so the variable of pH-dependent charge, that's due to this hydroxide that's sticking out, whether it's a part of an organic molecule, part of an oxide, or part of a phyllosilicate. And basically what we're looking at here, got white. Sorry about that. There should be a black line here. Okay, and right here you can see sort of where the white spots are there. Okay, there should be a black line here. Okay, as a negative charge, the negative charge that comes with this comes with increasing pH. So as I increase in the soil solution the hydroxide is going to be popping off that proton to make water, and as a result, I'm going to have more net negative charge associated with these hydroxides that are sticking out into the soil solution. And as a result, I'm going to get a more negative charge. Now, as the pH starts to drop, we start putting protons. See, there's the black line again. So we start seeing protons going into the soil solution. These protons are going to react with this hydroxide here, in essence making a water molecule and bringing a positive charge. So as the pHs drop, my charges become more positive. Now the consequence of this is that in this scenario, this colloid is going to be attracted to more positively charged ions because it has a negative charge. This is a negative magnet in essence. So cations, positively charged ions, are going to be attracted to it. So as the pH goes up, my soils can hold on to more positively charged ions. Things like calcium. As my pH is starting going down, I'm going to lose that negative and I'm going to start having a positive charged ion, positively charged attraction, which means my negatively charged ions are going to start to be attracted. My phosphates. Does that make sense? Okay. Questions so far? And I throw this, this is an older version of what's in your book, but I throw this in here so you can see this effective cation exchange capacity based on the pH. So as the pH goes up, my cation exchange capacity goes up for my pH-dependent charges. Question, go.
Going to the back, the last slide, could you give an example of some more cations that, and where those might fall of different nutrients like calcium?
Oh, okay, so any of the positive charge. Okay, so the question was, can I give an example of more of these charged ions? Hold on to that question because, in fact, that's what the whole next part of this lecture is about. Okay? So what kind of ions would be a good representation of something that would be a negatively charged ion versus what would be a really good example of a positively charged ion that would be attracted to this negatively charged colloid? Question?
So in this picture right here, the solution is basic, and so then the molecule becomes acidic?
Yes, so the pH of the soil solution is increasing, so it's becoming more basic, okay? Because I'm increasing the concentrations of the hydroxide, which means I'm neutralizing the protons, okay? So as a result, this molecule wants more protons because it wants it, they want to balance these solutions. And so as a result, this proton's being pulled off the colloid at the edge and being turned into water.
So that means that the colloid is acting like an acid.
Actually, it's not. Okay, so the statement was the colloid is basically acting like an acid. And that's not really. It's actually acting more like a buffer. Okay, so it's buffering, and we haven't talked about buffers yet, but it's buffering the pH change by modifying the proton and hydroxide concentration, or mitigating it. Okay, so as I increase 1 protons, I'm going to have more hydroxides potentially in this, and that's so you see it's not really a hydroxide because it's not in solution. It's part of actually the colloid, but it acts like one, and the protons are basically attracted to it. So it's acting to buffer the proton concentration, the increase in proton concentration. Does that make sense? Go.
So does that mean that colloids don't have a pH as well?
The colloids themselves don't. They do. There's basically 3 pools of acidity in a soil. Generally, when we measure acidity, we're measuring the acidity that's in the soil solution. But there's also an acidity that's associated with the colloids, and that's at the surfaces. And then there's a pH that's associated actually with the material itself. Okay? And it's called total acidity, but for all practical purposes, from a biological systems perspective, the active pool, which is the pool that's in solution, is actually what we really are measuring and what we're really concerned with. Now, in the long term, when we start talking about fertility management, we actually are also very concerned about this reserve acidity that's sitting on the colloids itself, because this proton, as the soil solution increases, this proton can buffer by changing that hydroxide and turning it into water. So in a sense, this proton can act to prevent the pH from rising. Okay, because if I start adding more and more of these into the soil solution, what should happen to my pH? My pH should start rising, right? But if I have protons here that can come off of my colloid and bind onto this and neutralize the hydroxide by turning it into water, it's in essence resisting that pH change. That term is called buffering. I'm buffering the reaction. Does that make sense? So in a sense, yes, these colloids are in fact acids and bases, but not in the sense that you're using. You're thinking of an acid as, a proton that's like a sulfuric acid I put something on and it starts dissolving. Okay, does that make sense to everybody? Any questions on that? No? We feel good? Okay. This brings us to these 2 questions. Okay, and the first question is, well, if I'm talking about all these ions that are in solution, where in fact are they coming from? Okay, now this is not just the ions that are going into isomorphic substitution, but these are the ions that are actually exchanging on these exchange sites that we're producing because of the charged molecules, or colloids. Okay, and then the question is, and this goes to Kata's question earlier, can you give me some examples of some of these ions? Well, which of these ions in fact do bind to these exchange sites? Okay, so if I have a negatively charged particle, I'm definitely not going to be too attractive to other negatively charged particles that are in the soil solution. The ions, I should say. Does that make sense? But I will be attracted to positively charged ones. So let's start with the first one. Almost all the ions or molecules that are in the soil are either sorbed by the roots in the long run, are either sorbed by the roots, they're taken up into the plants, or they're leached away. Those are the two things that are going to happen to them. Now, in the interim, though, they can be held in the soil by cation exchange capacity, the ability of this soil to hold on to these things. But for these things to be absorbed by the roots or to be leached away, first, the ions themselves must be released into the soil solution. Okay? Now, this can happen because cation exchange, i.e. coming off of and being exchanged onto these colloids, and also anion exchange, the same thing, except this is a positively charged ion and this is a negatively charged ion. Okay? I also can have ligand exchange, and I'll explain what each one of these are in a moment. But ligand exchange is basically you're looking at an ionic or covalent bond that's actually multiply binding to a central ion. So it's a metal usually. Okay? We can also have dissolution precipitation type of reactions where like calcium carbonate, I throw calcium carbonate into acid and it starts to dissolve. And then lastly, I can have something that's called surface chelation, and it's actually a ligand bonding type of reaction, but it's a very specific one and it's associated with organic molecules. Okay, so let's start with a cation exchange. Clays have this negative charge, that comes from that isomorphic substitution. And organic matter also has this negative charge, and it has to do with the carboxylics. Cations are loosely bonded through sort of electromagnetic attraction to these particles. Okay? These particles, or I should say not the particles, but the ions themselves can exchange. Now, this is not an ionic bond. This is just an I mean, you can think of those magnets. You know, I can get it, and it could be really tightly held, but I can still pull them apart. They're not the same object. Okay? So if I put another magnet into the system, a stronger magnet, for example, that magnet could potentially bounce off the first ion that's held and exchange for it. Does that make sense? Okay. So here's my soil colloid. Here's a calcium that's being held on to this colloid. I start raising the magnesium concentration in the solution. This magnesium could literally take this calcium and bounce it off, put the calcium in solution, and be replaced by magnesium. Now, there's reasons why this is important, and you guys can, off the top of your heads, you probably can think of it right now as a sort of soil fertility, but remember me saying there's really only two places these ions are ultimately going to go. They're either going to go into the plant roots or they're going to be leached from the system. So why is this cation exchange capacity so important? Well, this exchange complex holds on to these ions until the plants are ready for them. Okay? If I throw a lot of fertilizer on and the plants can't take it up, where's that fertilizer going to go? It's going to be leached right out of the system, the second option for this material. As a result, these exchangeable ions are not leached from the system, but they are not leached away from the roots, in essence. Okay, so if I have a volume of soil, okay, and here are my roots in this soil volume, and this soil volume is holding on to these materials, okay, they're going to prevent that stuff from being leached away, and they're going to keep it in the proximity of the roots. Does that make sense? Okay, which I just heard my phone, which means I forgot to turn it off. Sorry. The other cool thing about this, remember, because these things can be exchanged, these ions, when the plants start wanting them or need them, are rapidly exchangeable. Okay, the plants literally have the ability to start pushing ions out into soil solution. Those ions then compete for the exchange sites. They release the ions that are on those exchange sites, put it into the soil solution, and the plant can then harvest it. Many more cations reside on the exchange complex than in the solution. Okay, so if you think about this soil solution here, here's the soil solution, and here's the colloid. There are a lot more of these ions that are sorbed on to the exchange sites on the colloid than are in the soil solution. And that's a good thing, because if they're out here and they're not being taken up by the plants, they are being leached. They're moving with that water. And lastly, and this is sort of more, you guys know that I'm interested in heavy metals and things like that, not the bands, but this type of ion exchange can actually purify a metal polluted water or soil. Okay? It's not going to purify the soil, but it will purify the water that in fact has the contaminants in it. You run the water through the system, the water brings in the contaminants, the soil then basically binds, because all these metals are ions and they're charged, and soils in essence can be the charged particles that can then be attracted to the colloids. Go.
You know, I was just thinking about the lead in Dillman Farm. So as you add the compost to it, will you eventually bury it and it'll be part of that, whatever process, and that would?
Yeah, so the question was, if you keep adding organic matter, so in Dillman, remember Dillman having the lead arsenate. If you keep adding organic matter to Dillman Hill, will you in essence bury that material? In a sense you will, but in a sense you won't, because that organic matter is being decomposed. Okay, so as I bring more organic matter in, I'm certainly increasing to a certain extent the organic matter composition of those soils, but I'm going to get to a point where decomposition rates are going to be just as fast as accumulation rates, at which point I'm sort of have stabilized my organic matter. Okay, the organic matter will in fact also, and we'll talk about this when we talk about chelation, but the organic matter also will bind these heavy metals in addition to the colloids sorbing them. Okay, but let's hold off on that one when I start talking about chelation. Okay, go, question.
For the number 5, that would only hold,
True if the metals were soluble in them.
well, and it would be pH dependent.
It would be pH dependent, and so the question is, this would only work for certain scenarios because metals are more or less soluble in water based on the pH, and the lower the pH, the more lead, for example, is soluble. Okay, so if I have a low pH material, I'm going to have soluble lead that's going to move into these soils. But if the pHs were neutral, in all likelihood, the lead is not going to be moving with the water because it's not soluble. And that's one of the benefits at Dillman Hill, for example. The reason those leads are the lead is staying in the soil is twofold. One is I've got clays in there that have good cation exchange capacity, but two, the water that's moving through the system is not very acidic, and so as a result, the metal, the lead, is not soluble, which means it's not leaving the system through leaching. Does that make sense? Okay. All right. So cation exchange, what in fact controls this ion exchange? Okay, it's important. We got 5 nice reasons here why it's important, but actually what is actually controlling that exchange? And the exchange is basically controlled by 4 things. Here's the first three. The first one is cation selectivity. It turns out if you think about those magnets, the larger the magnet, with the same charge, the larger the magnet, the tighter it's going to be held by the soil. Okay, by my other magnet, okay? So here we have a potassium versus a lithium. Okay? The potassium, because of its larger shells, is less likely to be exchanged than the lithium. Now why? You got to think about the nature of these ions. Here's my colloid, whatever it happens to be, negative charge. All right? Here are 2 different cations. Okay? The positive charge is sitting right in the center. The negative charge is in the orbitals around it. Okay? So for this to be knocked out, for these ions to be knocked off of this surface, the positive charge has to be knocked off. The distance here between here and here versus here and here is significant. So as a result, it's harder for that positive charge to get in here to knock that out. It's a lot easier, if you look at that, for the lithium to be surrounded by protons, by water in essence, than the potassium. So the potassium, because it has a larger shell, it's more likely to hang on to those exchange sites. So the first rule is basically size. The bigger it is, the tighter it's held. The next one is the charge equivalence. And this totally makes sense. The higher the charge, the tighter it's going to be held. So if I have a +1 charge versus a +2 charge versus a +3 charge cation, the +3 charge cation is going to be more likely to knock somebody out and more likely to be held to stay on the exchange sites. Does that make sense? Okay. The third is the ratio law. This is basically, for lack of a better rule, we actually really more call this the mass action rule. But the more of one ion I have over another ion, the more likely that first ion is going to be in the exchange sites. Think about my soccer analogy way back. Okay? I have one really good soccer player and one really bad defender. Okay? In all likelihood, that soccer player is the offensive player is going, not offensive. The attacker is going to score the goal. But then what happens when I start putting 2 defenders on them? And then 3 defenders, and 4, and 5, and 6. Sooner or later, that mass, that just the sheer mass of ions is going to be able to knock out that other ion. Okay? For gamers, this is like a good analogy would be a Zerg attack. Does this mean anything to anybody? Okay. Basically, you just throw enough things at somebody, and sooner or later you're going to win. Bear with me. All right, so we got cation selectivity, we got charge equivalence, and we have the ratio law. Okay? The last one is what we call complementary cations. And complementary cations is basically, it's sort of a combination of all these things, but you have to imagine, let's use this board over here. Here's my charged surface, okay? And my soil solution is up here. This is the soil solution. And on this charged surface, I'm going to have a lot of different ions that are being held. Okay? Now, if on this charged surface I have something that's being held really tightly, plus, let's imagine this is a +3, and this is a +2. Okay, actually, make this a little bit. Oh, okay, +3 and a +2. Just use those two. In all likelihood, which one of those is going to be the one that gets bounced off? The 2. It's smaller than this, and it's got a less charge. Right? Okay, how about this, though? Plus. Which one's going to be more likely to be held there? This guy. This has got the charge benefit, right? It's got the same shells as these guys, but it's got a higher charge. Okay, which means when things come in to compete here, it's more likely to pop this guy off than this guy off. And it's more likely to pop this guy off. This guy over here is sitting pretty. So it's the combination of the ions that are on the site that are also going to contribute to what's going to get popped off, what's going to be exchanged. Does that make sense? Question.
Which is more important, the size of the cation or their charge? What if you had a bigger +2?
If I had a bigger +2 here, take this and turn this into a bigger +2. Which one? This one versus this one? Which is more likely to get knocked off?
The +2 and the small +3.
No, like that. So
The
the
big
small
+2 and the small +3, which
Yeah,
one
so
will
like-
survive?
Oh, okay, now I understand what you're saying. I actually don't know. I think it's going to have a lot to do with what's out here as well. Okay? But the reality is this is a combination of all these 4 factors that are going to be controlling this. Okay? The size, the charge, the number, and its arrangement next to whatever it's next to. Okay? So in this case, this guy is probably going to get kicked out first. I mean, we're looking at all of these at the same time. It's not like we're just picking on this guy. We're looking at the exchange. These guys want to exchange with all of these guys. They want a spot at the table or at the colloid. Okay, so in all likelihood, this is the one that's going to get knocked out first. These guys are probably, I'm not quite sure. I think it'll have depend on what shell this actually is. But I'm thinking that, it's probably a little bit of both. And then on top of that, if there's a lot of these +3s out here, if you start thinking about the mass action rule, okay, this one might be the one that gets knocked off, but it's going to get replaced with the same thing. Okay, so it's a combination of all 4 of these that are controlling that cation exchange. Go.
I'm confused about the first one. If you have a really big cation and you have lots of negative shells, wouldn't that make it more weakly held because the positive charge is greater?
You would think so, but what happens is it's not like here, let's use this one. It's not like the ion is sitting like this. The ion is actually sitting like this. with a positive here and the electrons out here. Which means if I have an ion that's out here that wants to exchange for this guy, it's basically the entire body has to get inside this to knock it out, because it has to go through all of these electron orbitals as well. Okay, now granted, these orbitals are going all over the place, so as it gets closer and closer and closer, the electrons are going to be more concentrated on this side of it. But this is happening really, really fast. So as this thing is moving in, it's got a bigger force field. What am I trying? How do I explain this in a different way? It's this that's being attracted to this. Okay. Now these ions that are in here, they're positively charged, but they still have these electrons. They still have some negative orbitals going around them. Okay. So they need to get that positive close to this, and if this is in the way, the distance that they're going to be attracted is this far, versus one that's like this, it's only going to be this far. Does that make sense? Yeah? Another way to think about it is sort of these magnets coming closer and closer together. You notice how you get closer and closer together towards the other magnet. It gets harder, it gets stronger and stronger and stronger. Well, this magnet is just being held, is preventing everybody else from getting very close, so it's not attracted as much. Does that make sense? Yeah? Okay. Go.
So since some ions are held tighter, is there sort of like an eventual equilibrium that happens at all, or is it just?
That's a good question. So the question is, if some of these ions are held more tightly than others, do I in fact ultimately reach an equilibrium? And as long as I don't change, so let's go back to this drawing. So if we imagine I have an entire soil, okay, and in a little part of that soil we're looking at this colloid coming out here, right? Okay, so the solid is here, a negative charge, net negative charge, and this is all soil solution out here. This is the pores. Now there's another colloid over here, and so on and so forth, right? Okay. Depending upon what the concentration is out here, I'm going to get into an equilibrium. But you have to imagine what's going on in this entire soil. Okay, as things get pulled out of equilibrium and into this location, I'm changing the concentration gradients around here. And so other things are going to start moving into this. And so there's going to be so you can sort of say, okay, potentially I could reach a dynamic equilibrium. But we are operating on a terrestrial system, so there is always some sort of event coming in, a rainstorm. It starts to rain, it's going to be bringing in more protons because rainwater is naturally acidic. So I'm going to be changing the proton concentration. Okay. As the organic matter up here decomposes, I'm going to be putting more ions into solution. So I'm changing this dynamic, this soil solution. And as long as I'm changing that solution, this is going to be dynamic. I fertilize. You can think of a lot of different scenarios. Now, yes, we have a closed system. We certainly can create this dynamic equilibrium where we basically have X amount of something here and X amount of something out here. Okay? But even in that scenario, these guys, calcium here is exchanging with calcium out here. It's not like these guys stay in solution and these guys stay here. Does that make sense? Okay, question.
So in the example of the heavy metals in a clay soil,
Mm-hmm.
if you put organic material on top of that and you have acidic rains, would that mean that the metal is held less tightly?
So the question is, this is sort of, in a sense, kind of a remediation technique. Okay, if I have a clay soils like the not like the Hudson soils, okay, and it's holding on to lead, okay, what happens if I put organic matter on the surface? Well, I think that I wouldn't probably put the organic matter on the surface. I'd probably put it down below around here or integrate it in, because with the rain system and I start raising the pH or lowering the pH, I mean, let's talk about lead, we want to lower the pH. The system is going to be driving stuff this way. It's not going to be driving it back up towards the organic matter. So if I wanted to use the organic matter to hold on to these metals, I'd probably want to put it into a better intimate contact with the contaminated material. In the system here, around here, the water flow dynamics is this way. Now, yes, there is some water flow dynamics this way because of root uptake, okay, but most of it is going this way. Now, if I was starting to think about something out west where it's a drier environment, and I start looking at this kind of mobility, you know, capillary action moving things up, maybe that might be a scenario. But from a remediation sense, I'm not actually remediating, I'm just moving. I'm moving it into the organic matter. But I would really have to lower that pH to be able to do that. Does that make sense to everybody? Does everybody understand the premise? Okay. You cool? And this is all this cation exchange is all possible due to the charged nature of these molecules. Okay. Anion exchange basically operates the same way, except it's negatively charged versus positively charged. It's generally much smaller than CEC. And it's basically the attraction of the negatively charged particles to a positively charged, the negatively charged ions to the positively charged particle. Now that positive charge can be due to pH dependent charge, though it also could be part of the permanent charge, as we talked about. Then there's ligand exchange. Okay? This is generally associated with amorphous and oxide minerals, but basically ligand, it's not an anion exchange, and it's very strong. It's a strong bonding, and it's very specific. This is not an electrostatic attraction. This can be an ionic or covalent bond. But basically what you're looking at is some sort of centroid element, or a metal, for example, where you're literally having these ions, these individual elements are literally sharing electrons at this point. They are now becoming a molecule. It's not an electrostatic attraction. Okay? So you can certainly imagine that this is a very strong bond compared to a cation exchange absorption. Does that make sense? So as a result, these are a lot more resistant to exchange because you literally have to break the bond. You don't necessarily have to put a different magnet in. Okay, does that make sense? Questions? No? Go. Well, they're using a phosphate example here, but literally this phosphate, this P through this oxygen is bonding to the aluminum. This is not a charge. So if we look at these guys up here, you know, these are charge attractions. I'm not sharing electrons. Okay? This guy happens to have a positive charge because it's missing an electron, and this guy tends to have more because they have more, but it's just like a magnet. Okay? This one, I'm literally sharing electrons. So the phosphate is literally, that PO4, this phosphate with one of these oxygens, in this case this one, is literally binding to the aluminum. Okay, so this aluminum is a centroid bond. Okay, now let's skip this for a second because we might as well talk about surface chelation as well, because the same effect is happening here. In this case, we're looking at a colloid. Okay, in this case, with chelation, we're looking at an organic molecule doing the same thing. But the interesting thing about the chelation is we're looking at multiple ligand bonds, okay, which makes it even more difficult to get that iron off the system. Okay, in this case, let's start from the first one. If I had iron, and we'll use iron as the example. I'm running out of boards. Okay, here's my colloid surface. My iron +3. Okay, I still have electrons out here, but this is negative charge. Okay, this is a magnetic attraction. Okay, a ligand bond, on the other hand, I'm literally taking this oxygen here, okay, and binding it to an oxide, for example. This is not electrostatic charge attraction anymore. This is an ionic or covalent bond. Okay? Now with chelation, in this case we're looking at this one. Just one bond here, one ionic covalent bond. With chelation, and we're looking at an organic molecule, I'm literally looking at 2 or more binding onto the iron. So think about this sequence. Which is the easiest to release? This is going to be the easiest to release because it's just an electrostatic attraction. This is going to be harder to release. This is going to be extremely hard to release because for this iron to be released, you literally have to break both of those bonds. Okay, chelation, a chela basically means like a eagle's claw. And so in essence, the way to think of this is I have a metal ion that's basically being clamped in place. Okay, does that make sense? Yeah, kind of? Okay, so for this guy to be released, you basically have to digest all of this before this guy is going to be released. The last one is this dissolution precipitation one. I'm literally putting in calcium carbonate, for example, and I'm putting acid into the solution, and I basically put the ions into solution. Now I've got a calcium available and I've got a carbonate available. Okay, makes sense? Pretty straightforward, that one. Okay, so at this point we have a fairly good idea about where these ions come from, and we have a somewhat to a good idea about how these ions actually bond to the exchange sites. Okay, we have electrostatic charges, and we have the rules that control that. We have ligand bonds, and then we have sort of the chelation, sort of expanded ligand bond, and then we also have disillusionment. Okay, now I put this up here, this nota bene. I put this up here because I want you to realize that the environment that this is occurring in is extremely, extremely dynamic. And this goes to Andrew's question earlier. You know, do these things come into equilibrium? Well, they do, but it's a very temporary equilibrium. Anytime some kind of stochastic event comes in, anytime you start seeing decomposition of organic matter, you're going to change the concentration of these ions that are in the solution. And the minute they start changing, they're going to start changing the composition of what's at the cation exchange sites. Okay, because they're going to start exchanging with it. Right? Okay, so let's actually talk about what that cation exchange site means. What is CEC? What is cation exchange capacity? How do we quantitatively measure this capacity of a soil to hold on to these cations or potentially anion exchange capacity? How do we measure a soil's ability to hold on to anions? Cation exchange capacity is basically just a measurement of the total amount of exchangeable cations a volume of soil can hold on to. Okay? And we basically use milliequivalents because we're interested in the charge. Okay, so it's moles of charge, okay? Amount of charge, okay? So example that I show here is one potassium ion with a +1 charge is equal to a half of a calcium charge because it has a +2 charge, right? So 1 calcium would be equal to 2 potassium. Does that make sense? We're looking at the charges. This has 2 charges, this has 1 charge. So calcium is equivalent to, potassium is equivalent to 1/2 of a calcium charge. It's also equivalent to 1/3 of an aluminum charge because aluminum has +3. We're literally talking about charges here, how many positive charges you can hold on to. So if I had a molecule that I had a colloid that had a +3 charge, it could hold on to 1 aluminum, it could hold on to 3 potassium, and it could hold on to 1 calcium and 1 potassium. It couldn't hold 2 aluminums because it doesn't have the charge capacity. This charge is largely dependent on whatever that molecule is, determined by the clay and the organic matter or the content of that soil. Okay? I put this chart up here so that you can actually see the differences in CECs based on the material. If I have an organic matter, I'm looking at 200 to 1,000 milliequivalents charge-wise per kilogram. So it can hold up to from 200 to 1,000 charges in that kilogram. Okay, smectites, 90 to 150. Ilites and chlorides, now this is CEC, cation exchange capacity, 10 to 30. And then we get down to the kaolinites and the oxides, basically nothing. Okay, so the nature of the material is going to affect that CEC because it has to do with the permanent charge and the pH-dependent charge. But permanent charge is the big thing when we're looking in these guys. Now, give you a good example. Okay, the Mississippi going through here, okay, going down, right through in here, joining up, and then heading down to Louisiana. Okay, so basically you're looking in between the two rivers here. You know, take a look at this, and then take a look at this chart over here. Up here, small CECs, or small milliequivalents. As you go darker and darker and darker, your milliequivalents increase. So that means that my cation exchange capacity, as I get darker and darker and darker, increases. Does that make sense? Okay, now let's look at this landscape. And I want you to look at two spots. I want you to look basically at this really dark spot here compared to this really light spot up here. What type of materials do you think I have in this location if I have really high cation exchange capacity? You have a choice of two things, basically. I have lots of organic matter, or I have what? Clays. Clays and silts totally make sense if you think about this river system. This is the floodplain. When we go out onto the floodplain around here, when we were at Dillman this week, what kind of soils did we have? Silts and clays. Okay? When we were up at the higher elevations to the edges, we started getting into the sands. Okay, what is this? We talked about this earlier in the semester when we were talking about entisoils. And these were SAM ents. These are sandy. The nature of the surfaces, I have very few surfaces volume-wise. Okay? And I'm looking at silica oxide type of stuff. I'm not even looking at clays. So as a result, my cation exchange capacity in these sandy soils are greatly reduced compared to my silty clayey soils. And that's just, if we don't have to talk about the mineralogy there. Okay, we're just looking at the charges associated with the surface areas. Okay? Now, why is this important? If I'm a farmer, just because I'm growing crops here doesn't mean I can't successfully grow crops. But I have to think about my fertility management really hard and think about when and how much I'm going to be adding nutrients in this type of situation versus this type of situation. Well, just because I have a high CEC doesn't necessarily mean I'm fertile. My soils are fertile. But it does mean that I have an ability to hold on to those nutrients much better here than I do here. Which means I have to be careful about how much fertility I add from a fertilizer sense to this location. Why? Those ions, those nutrients are going to go to two places. One is your plant roots, and ultimately the other one is leaching. Cation exchange basically defers that process. If I don't have high cation exchange and my plants aren't sucking it up as quickly as I put it in, where is it going to go in this scenario? It's going to go down the Mississippi and end up here. Right? Here, on the other hand, because I have such a high CEC, these soils have a very good ability to hold on to those nutrients temporarily until ultimately they're either taken up by the plant or leached away. Does that make sense? Okay. How do we measure this? Okay, I have a soil here. This is out of your book, but I have a soil, and I basically put it into a funnel. Okay, and what I do is I pour a liquid on top of it. In this case, I have an excess ammonium solution. I saturate it. Now remember these rules for exchange. The bigger ones will knock off smaller ones. High charges will knock off smaller charges. Big ones will knock off smaller ones. Okay, or I should say concentration, the largest amount. So what happens if I want to, in fact, figure out my cation exchange capacity? Well, I can take advantage of those rules, and I can basically throw in a really big one, or I can throw in a high-charged one, or I can just throw in a lot of something and knock everything out. Okay, so in this scenario, I'm throwing in a solution that has a high concentration of ammonium. Okay, I throw it in here. Okay, ammonium's also rather large. It only has a +1 charge, but because I'm just using so much of it, I basically saturate the system and I'm knocking everything else off. Make sense? So in this scenario, basically what I'm doing is I'm driving the system so that all the exchange sites have ammonium on it. I'm knocking everything else that comes out into solution. Make sense? Okay, now at this point, I still don't know what the CEC is. What I do next is I throw another solution in with a different ion. And that next ion basically is going to drive out all of the ammonium and replace it with potassium. But what I'm going to get is a pure solution of ammonium, and I can measure how much ammonium is in here, and it can give me an idea about what the CEC is of my initial soil. Now, why do I do that? Why don't I just measure this and measure everything except ammonium? I have a mix of different charges, and the reality is there could, in fact, be ammonium in here. The ammonium could be present in this soil. We got this from the real world, right? So I basically drive it out, saturate the system in this, then drive that out, and measure the concentration. Okay? The other important thing here is just because I have the CEC, just because I have that amount, doesn't actually mean that all of those sites are actually occupied by cations. And this is where we get into a concept that's called base saturation. Okay? I have a total ability to store nutrients, but just because I have, imagine this, okay, I have a volume of soil, okay, and it has the ability to hold on to 100 charges, positive charges, right? Does it mean that all of those charges are in fact going to be occupied by cations that are nutrients? Okay? I want to have a good measure about how much of that cation is of that cation exchange capacity is actually occupied by nutrients. Okay? So I think I missed a jump here, but okay. So base cations, you've heard me use this term before. Base cations are basically calcium, magnesium, potassium, and sodium, or other non-acid cations versus acid cations. Base cations, when I say base cations, these are not technically bases. They are basically non-acid base cations that serve as bases, because what they do is they act to neutralize the protons. Okay, so if we read this, technically these are non-acid base cations. But they do serve to reduce the acidity, so they serve as bases. You guys know what a base is? You know what an acid-base combination is? Okay, so here is sulfuric acid. Does that look familiar to everybody? We're over time. Oh, that would be why I'm off. Okay, guys, be free. I will see you on Wednesday. Thank you for reminding that.